I want to begin with a thought experiment. You are standing on the surface of Mars. The ground beneath your feet is red iron oxide, cold, dry, sterile. The sky is a pale butterscotch color, thin and hostile. You have been here for 18 months. The mission is complete, the science is done, and now you want to go home. The problem is that right now, today, at this specific moment in the relative positions of Earth and Mars in their orbits, Earth is on the wrong side of the Sunday. The orbital geometry is unfavorable. Launching now would be expensive in fuel and potentially impossible with available propellant. You have to wait. You wait 6 months. Then you wait for the next launch window. You wait another 14 months. You have now been on Mars for 2.5 years, and you are just beginning the journey home. This is not a hypothetical problem for a distant future mission. It is the specific physical reality of any human mission to Mars with current or near-term rocket technology, the physics of orbital mechanics, the specific gravitational geometry of the inner solar system, and the biological reality of what prolonged spaceflight does to the human body, combined to make a round trip to Mars one of the most challenging and dangerous endeavors in the history of human exploration. And unlike the dangers of the journey, which can in principle be engineered around, some of the fundamental constraints are set by the laws of physics themselves. I want to take you through all of them. Not to argue that Mars missions are impossible, they are not. But to be honest about what the laws of physics actually require, what the biology actually permits, and what the gap between our current capabilities and those requirements actually looks like. Because the popular narrative about Mars settlement has systematically understated the difficulty in a way that I think does a disservice to the seriousness of the challenge. Let me start with the orbital mechanics, because they set the fundamental timing constraints that everything else must accommodate. Mars orbits the Sun at an average distance of 1.52 astronomical units compared to Earth at 1 astronomical units. Mars has an orbital period of 686.97 Earth days, approximately 1.88 Earth years. Earth has an orbital period of 365.25 days. Because the two planets orbit at different speeds, the angle between them changes continuously. The geometry repeats approximately every 780 days, which is the synodic period of Mars, the time between successive oppositions when Earth, Sun, and Mars are aligned. Let me derive why the synodic period is 780 days, because the derivation reveals the fundamental orbital geometry that constrains every Mars mission. Earth completes one orbit in 365.25 days, meaning it moves at an angular rate of 360 degrees per 365.25 days, or approximately 0.9856 degrees per day. Mars completes one orbit in 686.97 days, moving at approximately 0.524 degrees per day. The difference in angular rates is approximately 0.4616 degrees per day. For Mars to gain a full 360 degrees on Earth, starting from any configuration, takes 360 divided by 0.4616, approximately 780 days. This is why launch windows occur every 780 days, roughly 26 months. The synodic period of 780 days sets the basic rhythm of Mars missions. Launch windows occur approximately every 26 months. Not every launch window is equally favorable. Mars has a notably elliptical orbit with an eccentricity of 0.093, compared to Earth's 0.017. This means Mars's distance from the Sun varies between 1.38 and 1.67 astronomical units, a variation of approximately 21%. When Mars is at perihelion, closest to the Sun, and Earth is also positioned favorably, the minimum transfer distance is much smaller than when Mars is at aphelion. The most fuel-efficient trajectory from Earth to Mars is the Hohmann transfer orbit, named after Walter Hohmann, who described it in 1925. A Hohmann transfer is an elliptical path that is tangent to Earth's orbit at its perihelion and tangent to Mars's orbit at its aphelion. A spacecraft on a Hohmann transfer leaves Earth orbit with a specific velocity boost called the trans-Mars injection that puts it on the transfer ellipse. It coasts on the ellipse for approximately 259 days, then decelerates to enter Mars orbit. The Hohmann transfer is optimal in the sense that it minimizes the total velocity change required for the transfer, but it is only strictly optimal for circular coplanar orbits. The actual orbits of Earth and Mars are elliptical and slightly inclined relative to each other, so real missions use trajectories that are optimized numerically for the actual orbital positions at the specific launch date. Here is the critical constraint on the return trip, and it is one that deserves more attention than it typically receives. When you arrive at Mars after a Hohmann transfer, the geometry of the inner solar system is such that Earth has moved to a specific position in its orbit. For the return trip to also be a Hohmann-type transfer, you must wait for Earth to be at the right position for the return window. This takes approximately 14 to 16 months from arrival, depending on the specific mission profile. If you arrive at Mars in the summer of 2033, for example, the return window opens approximately 15 months later. If you want to leave before that window, you need a faster, higher energy trajectory that requires dramatically more propellant. If you want to leave after that window, you wait another 26 months for the next window, spending a total of 40 months on Mars. There is no option between these. You go in the window or you wait. The minimum stay on Mars for a round-trip mission, accounting for the outbound transit, the surface stay, waiting for the return window, and the return transit is approximately 500 days. The total mission duration from Earth departure to Earth return is approximately 900 days, roughly 2.5 years. This is not a choice. It is the physics of orbital mechanics applied to the geometry of the inner solar system. The Tsiolkovsky rocket equation makes the timing constraint even harder. If you want to launch outside the optimal window, you must carry more propellant to handle the less favorable trajectory. For a Mars return mission, the propellant required scales exponentially with the departure from optimal. A trajectory that departs 1 month early might require 20% more propellant. A trajectory that departs 3 months early might require twice the propellant. At some point, carrying more propellant becomes impossible because you cannot launch a vehicle of sufficient mass, and the constrained optimal window is the only practical option. NASA's reference mission for human Mars exploration uses a conjunction class trajectory, which minimizes propellant requirements by taking advantage of the favorable geometry during the stay. The surface stay in a conjunction class mission is approximately 500 days, and the total round trip is approximately 900 days. This is the baseline that all serious Mars mission planning starts from. Now let me take you to the biological problem, because 900 days in space and on Mars is not just a logistical challenge. It is a physiological assault on the human body that current medicine can only partially address. The most immediately dangerous aspect of a Mars mission is radiation. Let me describe the radiation environment in detail, because the two primary sources are very different in character and require different approaches to address. The first source is solar energetic particles, or SEPs. During solar flares and coronal mass ejections, the sun ejects large numbers of energetic protons and heavier ions. The particle flux during a major solar energetic particle event can increase by a factor of thousands above the background level. These events are somewhat predictable with advance warning on the scale of hours to days, but not reliably. The primary way to protect against SEPs is shielding, because the particles have relatively low energy and can be stopped by modest amounts of material. A small water or polyethylene storm shelter within the spacecraft can reduce the SEP dose substantially during an event. The second source, galactic cosmic rays, is much harder to shield against. Galactic cosmic rays are charged particles, predominantly protons and helium nuclei, but also heavier ions, including iron, that are accelerated in supernovae and other violent astrophysical events outside our galaxy. They arrive isotropically from all directions, with energies ranging from below 1 GeV to above 100 TeV per nucleon. At these energies, they can penetrate many meters of any material. The specific hazard from heavy galactic cosmic ray ions, called HZE particles for high Z and high energy, comes from their ionization density. When a fast, heavy ion traverses tissue, it deposits energy along a narrow cylindrical track, creating a dense column of ionization damage. The linear energy transfer, measured in kiloelectron volts per micron, for iron nuclei at typical cosmic ray energies is more than 100 times higher than for protons at similar velocities. This dense ionization creates clusters of DNA damage that are much harder for the cell's repair machinery to fix correctly than the sparse damage from X-rays or protons. The biological effectiveness of HZE particles, their ability to cause cancer relative to an equivalent dose of X-rays, is characterized by a factor called the relative biological effectiveness, or RBE. For galactic cosmic rays, the effective RBE is estimated at 2 to 5 for most endpoints, meaning a given absorbed dose of galactic cosmic rays is 2 to 5 times more damaging than the same dose of X-rays. This amplifies the health risk beyond what the raw dose numbers suggest. The radiation dose during the transit to and from Mars, roughly 300 days each way in interplanetary space, is estimated at approximately 300 to 500 millisieverts per transit, combining SEP and GCR contributions. For the full round trip, including the surface stay on Mars, where the planet provides roughly half the sky coverage as a radiation shield, and the thin atmosphere provides limited additional shielding, the total mission dose is estimated at approximately 1 to 1.5 sieverts. The current NASA career limit for astronaut radiation exposure is approximately 600 millisieverts for low Earth orbit missions, set to limit the increased lifetime cancer risk to below 3% using the BEIR7 risk model. A Mars round trip would exceed this limit for many astronauts. The actual cancer risk depends on the astronaut's age, sex, and individual genetic susceptibility. The ISS program has been operating for more than 2 decades with carefully selected crews and carefully designed mission durations to keep exposure below this limit. For a Mars mission, staying below the limit while achieving the required mission duration is not possible with current shielding technology. In 2023, NASA developed updated permissible exposure limits that use a career effective dose limit of 600 millisieverts with a 95% confidence level on the risk model uncertainty, rather than the previous approach. This updated framework affects the specific numbers but not the fundamental tension. The Mars round trip delivers a radiation dose that approaches or exceeds any reasonable safety limit derived from cancer risk models. The neurocognitive effects of galactic cosmic rays deserve specific attention because they are less well known than the cancer risk. Studies at NASA's Space Radiation Laboratory at Brookhaven National Laboratory, where accelerated iron and other heavy nuclei are used to simulate the GCR environment, have found cognitive deficits in mice after doses comparable to what Mars astronauts would receive. The specific findings include reductions in short-term memory, impaired spatial learning, decreased executive function, and increased anxiety-like behavior. The cellular mechanisms include direct damage to neurons from the HZE particle tracks, activation of inflammatory signaling in the central nervous system, disruption of synaptic plasticity, and reductions in the density of dendrites, the neural processes that form connections between neurons. These changes are not transient. They persist for months after exposure in animal models, and some are progressive rather than stable. The neurocognitive problem is qualitatively different from the cancer risk because it affects the crew's ability to perform the mission. Mars astronauts must make complex decisions under stress, troubleshoot technical problems, maintain social cohesion in a small group, and perform precise physical tasks, including EVAs in spacesuits on the Martian surface. These are the functions that the animal studies suggest are most vulnerable to GCR exposure. Arriving at Mars with measurably impaired cognitive function after 6 months of radiation exposure, and then accumulating more exposure over 500 days on the surface, is a specific and serious concern that the mission architecture must address. The second major biological problem is bone and muscle loss from microgravity. In zero gravity, the body no longer needs to support itself against Earth's gravitational field. The mechanical loading that stimulates bone density and muscle mass disappears. The body responds by losing both. On the International Space Station, astronauts lose approximately 1 to 2% of bone mineral density per month and significant muscle mass despite intensive daily exercise regimens of 2 hours or more. After 6 months on the ISS, astronauts typically require weeks to months of rehabilitation to walk and perform normal activities again. Their bone density, particularly in the lower extremities and spine, has decreased measurably. Their cardiovascular fitness has declined. Their muscle mass has decreased. The countermeasures, extensive exercise, nutritional supplements, pharmaceutical agents, reduce but do not eliminate these losses. A Mars mission involves approximately 300 days of transit in microgravity each way, plus whatever period is spent on Mars. Mars has a gravitational acceleration of 3.72 meters per second squared, 38% of Earth's 9.81. The effect of Martian gravity on bone and muscle loss is unknown. The threshold above which gravity is sufficient to prevent deterioration is not established. Animal studies suggest that partial gravity substantially slows but may not stop bone and muscle loss. Astronauts on Mars may continue to lose bone and muscle at a reduced rate throughout the 500-day surface stay. When the mission returns to Earth after 900 days, the crew would need to transition from Martian gravity, 38% of Earth's, to Earth's full gravity after a period of substantial physiological deconditioning. The rehabilitation required would be extensive, and the risk of fractures and cardiovascular complications during the transition would be significant. The third biological problem is fluid shifts and vision impairment. In microgravity, bodily fluids redistribute toward the upper body and head because there is no gravity pulling them downward. This increases intracranial pressure and causes a syndrome called spaceflight-associated neuro-ocular syndrome, or SANS. Approximately half of astronauts on long-duration ISS missions show structural changes to their eyes, flattening of the back of the eyeball, swelling of the optic disc, and folds in the choroid layer behind the retina. Some astronauts return with measurably worse vision that does not fully recover. The mechanism appears to involve increased cerebrospinal fluid pressure from the elevated intracranial pressure in microgravity. The long-term consequences of SANS are not fully understood, but for a mission lasting 900 days, the vision impairment could be severe enough to affect the ability to perform the required tasks. There is also the psychological dimension, which deserves more attention than it typically receives in engineering discussions of Mars missions. 6 to 12 crew members would spend 900 days in an extremely confined space, isolated from Earth by communication delays of 4 to 24 minutes each way, with no possibility of emergency rescue or resupply. The crew would face the knowledge that any major medical emergency, a severe illness, a psychiatric crisis, a serious injury, would have to be managed entirely with the resources on the spacecraft and with the skills of the crew. There would be no calling for help and receiving it in time to matter. Psychological studies of isolated, confined groups, from Antarctic overwinter stations to submarine crews to simulated Mars missions, consistently find that interpersonal conflict, depression, and reduced cognitive performance are significant problems that become more severe with mission duration. The 900-day duration of a Mars round trip exceeds the longest human spaceflight missions by a factor of 3 or more. And the psychological burden cannot simply be extrapolated from shorter missions. I have described the physical constraints as if they are problems that will eventually be solved by technology. Some of them will, some of them will not. I have described the physical constraints as if they are problems that will eventually be solved by technology. Some of them will, some of them will not. Let me now address the most fundamental enabling technology for the return trip, which is propellant production on Mars, because this is the hinge on which the entire return mission depends, and it deserves more detailed treatment than it typically receives. The physics of the return trip from Mars requires enormous quantities of propellant. A Starship-class vehicle returning from Mars to Earth requires approximately 1,200 tons of liquid methane and liquid oxygen. This propellant cannot be brought from Earth for 2 reasons. First, the mass of propellant required would far exceed the mass of anything that can be landed on Mars with current or near-term launch vehicles. Second, the Tsiolkovsky rocket equation means that carrying return propellant from Earth would require so much more propellant to get to Mars that the entire mission mass becomes impractical. The solution is in situ resource utilization, making the propellant on Mars from Martian resources. Mars has abundant carbon dioxide in its atmosphere, approximately 95% CO2 at a surface pressure of about 610 pascals, roughly 0.6% of Earth's atmospheric pressure. It also has water ice in subsurface deposits confirmed by radar measurements from the Mars Reconnaissance Orbiter. The Sabatier reaction converts carbon dioxide and hydrogen to methane and water. CO2 plus 4H2 yields CH4 plus 2H2O. The water can then be electrolyzed to produce oxygen and hydrogen. The oxygen is used as the oxidizer for the methane fuel. The hydrogen can be recycled through the Sabatier reactor. The net result is methane fuel and liquid oxygen oxidizer produced from Martian CO2 and water ice. This is real chemistry. The Sabatier reaction is industrial chemistry that has been performed for decades. Electrolysis of water is even simpler. NASA's MOXIE experiment on the Perseverance rover has already demonstrated the production of oxygen from Martian CO2 at small scale, producing approximately 10 grams of oxygen per hour from the Martian atmosphere during its experiments. But the scale required is staggering. To produce 1,200 tons of propellant in, say, 2 years before the crew arrives, you need to produce approximately 1.6 tons of propellant per day. MOXIE produces 10 grams of oxygen per hour. To scale from 10 grams per hour to the required rate requires a factor of approximately 10,000 improvement in throughput. You would need hundreds of industrial-scale MOXIE equivalent systems or a smaller number of much larger systems, all operating reliably on Mars for 2 years without human maintenance. The power required to run this propellant plant is substantial. Electrolysis of water requires approximately 3.5 kilowatt hours of electrical energy per cubic meter of hydrogen produced. For 1,200 tons of propellant, the total energy requirement is roughly 20,000 to 30,000 megawatt hours over the 2-year production period, requiring a continuous power output of approximately 1 to 2 megawatts. This requires either a nuclear fission reactor, the most reliable option for continuous power on Mars, or large solar arrays, which must be sized for the reduced solar intensity at Mars's distance from the Sun and for dust storms that can block sunlight for weeks. NASA and SpaceX are both pursuing designs for Martian power systems. A kilopower class fission reactor of a few kilowatts is far too small. Designs for tens of kilowatts to megawatt scale nuclear power systems for Mars have been studied, but none has been built and flight tested. The fundamental issue is not whether propellant production on Mars is possible. It is. The fundamental issue is the reliability requirement. The propellant plant must operate for years on Mars, unsupervised by humans, with no possibility of significant repair, and it must fill the return vehicle to the correct level, because if it fails or produces insufficient propellant, the crew cannot return. Before the first crewed Mars round trip, the propellant production infrastructure must be demonstrated to work reliably on Mars at the required scale. This requires sending uncrewed missions to Mars to set up, operate, and verify the propellant plant, monitoring it remotely through the 4 to 24-minute communication delay, and confirming that the tanks are full before committing to launching the crew. This infrastructure development is not a small step. It is a decade-long program of incremental demonstration missions, each building on the previous, each operating autonomously on another planet. The return trip from Mars is physically possible. The chemistry works, the energy sources are available in principle, but the infrastructure required to make it reliable enough to entrust with human lives is not yet built, not yet tested, and will require a sustained program of investment and development that currently has no committed funding or timeline. This is the honest picture of the physics and engineering of getting home from Mars. It is not impossible. It is hard in ways that the laws of physics make inevitable, and it requires solving specific problems that no technology has yet solved at the required scale. The radiation environment can be partially addressed by shielding, but shielding effective against galactic cosmic rays requires either mass sufficient to add substantially to the spacecraft mass, or magnetic shielding, which requires a superconducting magnet system generating a field strong enough to deflect GeV energy particles. Such a system has never been built and would require enormous electrical power. There is an alternative approach to the radiation problem that is worth describing: reducing the transit time. If the crew spends less time in interplanetary space, they accumulate less radiation dose. For a transit taking 300 days, the radiation dose is approximately 300 to 500 millisieverts. For a transit taking 90 days, it would be roughly 90 to 150 millisieverts. This is a meaningful reduction. Achieving a 90-day transit to Mars requires a faster spacecraft. The Hohmann transfer takes 259 days. To reduce this to 90 days requires a delta V of approximately 3.5 to 5 kilometers per second more than the Hohmann transfer, depending on the specific trajectory. This additional velocity change must be provided by propulsion. With chemical rockets, providing this much additional delta V requires a large increase in propellant mass, which then must be launched from Earth. The mass penalty makes a 90-day chemical rocket transit impractical for human-scale payloads. Nuclear thermal propulsion, which uses a nuclear reactor to heat a propellant such as hydrogen to extremely high temperatures and then expel it, can achieve specific impulse values of 800 to 900 seconds, roughly twice the specific impulse of the best chemical rockets. This doubled specific impulse allows the same velocity change with roughly half the propellant mass, or a given propellant mass, to achieve twice the velocity change. Nuclear thermal propulsion could realistically enable transit times to Mars of 100 to 150 days while remaining within reasonable mass constraints. NASA has been developing nuclear thermal propulsion concepts for decades, with intermittent funding and program starts and stops. The NERVA program in the 1960s and 1970s demonstrated nuclear thermal rocket performance at the engine level, achieving specific impulses above 800 seconds. Modern programs, including NASA's Draco demonstration mission planned for the late 2020s, aim to demonstrate the technology again at smaller scale. Nuclear thermal propulsion is not exotic physics. It is established engineering that has been demonstrated at the component level. The barriers are political, regulatory, and financial rather than fundamental. A nuclear thermal upper stage for a Mars mission would require licensing for a nuclear reactor in space, a process that involves the NRC, international treaty obligations, and public acceptance concerns that have historically been difficult to navigate. Nuclear electric propulsion, which uses a nuclear reactor to generate electricity that powers ion thrusters, offers even higher specific impulse, 3,000 to 5,000 seconds, but at lower thrust levels. Ion thrusters produce very little force per unit power, which means nuclear electric propulsion is practical only for small payloads or for missions where a very long thrusting time is acceptable. For a human Mars mission, where you need to deliver tens of tons of payload on a schedule measured in months rather than years, nuclear electric propulsion is not the right technology. The physics of propulsion sets hard limits. Chemical rockets cannot reach Mars in under 150 days without impractical propellant masses. Nuclear thermal rockets can reach Mars in 100 to 130 days with manageable propellant masses. Nuclear electric propulsion cannot practically achieve short transit times for human-scale payloads. These constraints follow from the specific impulse values and thrust levels of each propulsion type, which are ultimately determined by the energy density of the fuel and the efficiency of converting it to kinetic energy. There is one other propulsion concept that deserves mention: nuclear pulse propulsion. The system studied under Project Orion in the 1950s and 1960s, in which nuclear bombs are detonated behind the spacecraft and the pressure wave accelerates a large pusher plate. The specific impulse of nuclear pulse propulsion is estimated at 3,000 to 100,000 seconds, depending on the bomb design, and the thrust is high enough to move large payloads quickly. Transit times to Mars of 30 to 90 days were calculated in the Orion studies. The reason nuclear pulse propulsion has not been developed is the Partial Test Ban Treaty of 1963, which prohibits nuclear explosions in space. Amending or circumventing this treaty would require international agreement that is currently inconceivable. Nuclear pulse propulsion remains a physically credible but politically and legally unavailable option. The microgravity problems can be addressed by providing artificial gravity through rotation. A spacecraft rotating at an appropriate angular velocity can simulate a gravitational environment. The required rotation rate and radius to produce one Earth gravity is determined by the centripetal acceleration formula, G equals omega squared times r. For a comfortable rotation rate of 2 revolutions per minute, the required radius is approximately 225 meters. For current spacecraft designs, this implies either a very large structure or the acceptance of higher rotation rates that can cause motion sickness. None of these technical solutions is impossible. All of them are expensive, complex, and untested at mission scale. The gap between where we are today and where we need to be for a safe human Mars round trip is not a gap of years or decades of steady, incremental progress. It is a gap of fundamental capability that requires specific programs of technology development, each requiring sustained investment over years to decades. The orbital mechanics will not change. The geometry of the inner solar system is fixed by the laws of gravity. The 900-day round-trip minimum is a consequence of the orbital periods and eccentricities of Earth and Mars, quantities that are as fixed as the speed of light. No propulsion technology, short of something dramatically faster than chemical rockets, changes this. The radiation environment can be partially addressed by shielding, but shielding effective against galactic cosmic rays requires either mass sufficient to add substantially to the spacecraft mass. Polyethylene and water are among the most effective shielding materials, but they are heavy or magnetic shielding, which requires a superconducting magnet system generating a field strong enough to deflect GeV energy particles. Such a system has never been built, would require enormous electrical power, and its effect on the human occupants of the spacecraft is not established. The microgravity problems can be addressed by providing artificial gravity through rotation. A spacecraft rotating at an appropriate angular velocity can simulate a gravitational environment. The required rotation rate and radius to produce one Earth gravity is determined by the centripetal acceleration formula, G equals omega squared times r. For a comfortable rotation rate of 2 revolutions per minute, the required radius is approximately 225 meters. For a spacecraft with current mass and volume constraints, this implies either a very large and expensive structure or the acceptance of rotation rates above the human tolerance threshold for motion sickness, typically around 4 to 6 revolutions per minute. None of these technical solutions is impossible. All of them are expensive, complex, and untested at mission scale. The gap between where we are today and where we need to be for a safe human-Mars round trip is not a gap of years or decades of steady incremental progress. It is a gap of fundamental capability. Let me now connect this to the bigger picture I want to develop, which is about what the physics tells us about the cost of leaving Earth and why that cost is not going to zero as technology advances. The fundamental constraint on space travel from Earth is the tyranny of the rocket equation, which I described in the previous video about Proxima Centauri. The rocket equation says that the ratio of initial mass to final mass grows exponentially with the ratio of the desired velocity change to the exhaust velocity. For any mission that involves landing on a planetary body and returning, the velocity changes required are enormous. To land on Mars and return to Earth requires approximately 3 separate delta-V maneuvers: the trans-Mars injection to leave Earth orbit, the Mars orbit insertion, the descent to the surface, the ascent back to Mars orbit, the trans-Earth injection to leave Mars, and the Earth entry. Each of these requires fuel. The fuel for each maneuver must be carried from the previous one. The exponential growth of required fuel mass with total delta V makes the mass of propellant required for a round trip many times the mass of the payload. SpaceX's Starship is designed with the explicit goal of refueling in orbit and on Mars to address this problem. The plan involves launching the vehicle to Earth orbit, refueling it with multiple propellant tanker flights, then flying to Mars, where a propellant manufacturing facility on the surface would produce methane and liquid oxygen from Martian resources, carbon dioxide, and water through the Sabatier reaction and electrolysis. The vehicle refuels on Mars and returns to Earth. This is a technically coherent plan. The chemistry works. The Sabatier reaction, CO2 plus 4H2 yield, CH4 plus 2H2O, has been demonstrated at laboratory scale and is being developed at pilot scale. The water ice resources that would supply the hydrogen have been confirmed to exist in subsurface deposits across Mars. The electrolysis of water to produce oxygen and hydrogen is straightforward chemistry, but the scale required is enormous. A Starship-class vehicle requires approximately 1,200 tons of propellant for the return trip from Mars. Producing this quantity of propellant on Mars requires a large-scale industrial plant. Energy sources capable of producing tens of megawatts of power, water ice mining and processing equipment, and all of this must be set up and operating before the crew arrives without human maintenance for years. The infrastructure required before the first crewed round trip is substantial by any measure. The first humans to land on Mars will face a specific question that the physics frames clearly. Are you certain that the propellant production facility has operated correctly, that the propellant tanks are full, and that the ascent vehicle is functional? If any of these is false, there is no return. The first Mars mission, if it is a round trip, is betting human lives on the reliability of a propellant production system operating autonomously on another planet, tested only by remote monitoring and a one-way communication delay of up to 24 minutes. This is not a reason to not go to Mars. It is a reason to be precise about what going to Mars and returning requires, and to be honest about the specific points at which the physics creates irreversible commitments. The return trip from Mars is impossible with current technology in the straightforward sense that we do not have the infrastructure to produce propellant on Mars. When that infrastructure exists, the return becomes possible, but not easy. The 900-day round trip, the radiation exposure, the bone loss, the fluid shifts, and the psychological burden remain. These are the costs set by the physics of the inner solar system and the biology of the human body. Technology reduces some of them. It does not eliminate them. I want to close with a reflection on what this tells us about the nature of human expansion into the solar system. Because the Mars case is not unique. It is a template. Every destination beyond Earth presents the same structure. Orbital mechanics that fix the timing and duration of round trips. A radiation environment that is more hostile than Earth's surface. A gravitational environment that is different from the one human physiology evolved for, and a distance that makes rescue and resupply either difficult or impossible. The Moon is the easiest case. 3 days each way, the Earth's magnetosphere provides partial protection during transit, and emergency return is always possible with available technology. It is not easy, but it is manageable. The Apollo missions returned their crews safely, though with significant physiological consequences that were acceptable given the short mission durations. Mars is the next step, and the step is much larger than the distance in kilometers suggests. The orbital geometry makes it a 900-day commitment. The radiation environment is 3 to 4 times worse per day than low Earth orbit. The gravity is 38% of Earth's unknown in its long-term physiological effects. The communication delay makes real-time emergency support from Earth impossible. All of these are facts that the physics will not change regardless of the technology applied to them. The asteroid belt, Jupiter and its moons, Saturn and Titan are further steps in the same direction. Each one is harder than Mars for the same reasons, amplified by greater distances, longer mission durations, and more extreme radiation and gravitational environments. The physics of the solar system has not been arranged for our convenience. The nearest potentially habitable destinations, if they are habitable at all, are years away in transit time, require radiation exposures that exceed current safety standards, and demand self-sufficiency that no human mission has ever achieved. Getting home from Mars might be impossible with current technology. With future technology, it will be very difficult. The physics says so. If this changed how you think about Mars missions and the future of human space exploration, if the 900-day round trip and the radiation exposure and the propellant production requirements look different after understanding the orbital mechanics and biology, tell me in the comments. Tell me whether you think the barriers are primarily technological, primarily economic, or primarily physical, and why the distinction matters. Tell me whether the difficulty makes you more or less optimistic about humanity becoming a multiplanetary species within this century. And subscribe if you want to keep going into the places where the physics of the solar system meets the most ambitious and most difficult projects in the history of human exploration,